Greetings. So welcome to today's class. Just as a quick recap, we were dealing with the design of the closed-loop control system by applying the Rhodes criteria, and we did one example. So today, let's essentially learn the process of using the Rhodes criteria by doing another example. Right? So we will consider the plant whose transfer function is 1 by s squared plus 1. So we will shortly learn how do we use this in the control design process. So 1 by s squared plus 1 is the plant transfer function. So the input is u of s, output is y of s. Okay. So what we have is the controller transfer function e of s, and we have the reference input r of s. So what we do is that, like, we want to look at unity negative feedback. So this is what we have. Right? We have plotted in this particular area. So once again, we try out different controllers, and then we'll see which controller. Okay. So to begin with, let's first try out the proportional controller. If we recall, the transfer function of the proportional controller C of s is Kp. So then the forward path transfer function V of s is going to be equal to C of s times P of s. So that's going to be Kp divided by s squared plus 1. Okay, so that's what we have. Right? So given this, we want to get the closed-loop transfer function. So that's going to be y of s divided by r of s. That's going to be the closed-loop transfer function. So that is going to be equal to g of s divided by 1 plus g of s. Okay, that's what we have. So if we substitute for g of s, h of s is with 1. So we'll get Kp divided by s squared plus 1 divided by 1 plus Kp by s squared plus 1. And so if we take the LCM in the denominator, we will get Kp divided by s squared plus Kp plus 1. Okay, so this is what we will have as the closed-loop transfer function. Correct? Yeah. So immediately we could observe the closed-loop characteristic equation. That's going to be equal to s squared plus Kp plus 1 equal to 0. So what can we observe if we use the Rhodes criteria? So we can observe that this is a second order polynomial. So yeah. And
but coefficient of s is 0.
Coefficient of s is 0, right? So essentially,
The P and I controllers will not work.
so if the coefficient of s is 0, right? What will happen is that, like, we will not be able to make the closed loop system as a stable system, right? Isn't it, from the Rhodes criteria, because the necessary condition for Rhodes stability will not be satisfied. Okay, so then what will happen is then, like, the bottom line is then the proportional controller would not stabilize the system. Okay, so that's the conclusion that one can draw, right? This closed loop. Okay, so we can see that in this case, with this particular plant, the proportional controller does not. So once again, we will go to the next one, right? So let's try out the PI controller. So for PI controller, the transfer function will be Kp plus Ki by s. So this we will get as Kps plus Ki, the whole thing divided by s, right? That's what we will have. So now, if we look at this, we are going to have the forward part transfer function g of s to be equal to C of s times P of s. So that will be Kps plus Ki divided by s. That's the controller transfer function. And then the plant transfer function is 1 by s squared. Okay, so we use this. So then accordingly, the closed loop transfer function, which is going to be equal to y of s by r of s, is going to be equal to g of s divided by 1 plus g of s h of s. So what we will have is that we will have kps plus ki divided by s times s squared plus 1. Then the whole thing divided by 1 plus kps plus ki, okay, divided by s times s squared. Okay, so this is what we'll have. Then if we take the LCM and simplify, what we are going to get is kps plus ki in the numerator. Okay, in the denominator we'll get s cube plus kp plus 1 times s if we take the LCM and ki. Okay, so that's what we'll have, right? So please note that s by s times s squared plus 1 will cancel off, right, in both the numerator and the denominator. So immediately we can observe that the closed loop characteristic equation in this case is going to be equal to s cube plus kp plus 1 times s plus ki equal to 0. So we can immediately see that this is a third order polynomial, right? Using the Raoult's criteria, what can be immediately observed from this third order polynomial?
Again, s square coefficient is 0. So
What is the consequence?
so it is
The
not no curve is.
So the consequence is that like a PI controller cannot stabilize the closed loop system, right? So that is the consequence. Okay. So we can immediately observe that the coefficient of s squared is 0. So consequently, we have the what to say, PI controller will also not be able to stabilize this closed loop system, right? Because the necessary condition of the Raoult's criteria is not satisfied. So even the PI controller doesn't work, right? So this closed loop. Okay, so that's the right. Okay, so then the third controller is the PD controller. So what is this PD controller? So if you consider the PD controller, it's going to be KP plus KDS, right? So I'm just writing it as KDS plus KP. Okay, so that's the PD controller. So then in this case, what will happen? The forward path transfer function is going to be equal to C of s times P of s. That's going to be equal to KDS plus KP divided by s squared. So that's what we'll have for the uh, forward path transfer function d. So then the closed loop transfer function is going to be equal to g of s divided by 1 plus g of s h of s. So this is going to be equal to kds plus kp divided by s squared plus 1. The whole thing divided by 1 plus kds plus kp divided by s squared. Right? This is what we do. Okay, so immediately if we take the LCM, we are going to get it as KDS plus KP divided by S square plus KDS plus KP plus 1. Okay, so that's what we have. Okay, in the denominator. Right, so I'm sure all of us can immediately observe this. Right, so that's the closed loop characteristic equation in this particular case is going to be x squared plus kds plus kp plus equal to 0. Right? So that's what we have. So now what can we observe? This is a second order polynomial, right? So, and it's a second order equation, correct? So what can we observe?
Um, it will be the same sign and non-zero. So PD would stabilize the system.
Uh, so we learned yesterday that for polynomials till order 2, right, will be basically the those criteria must be of the same, must be non-zero and of the same sign. Okay, so that's something which we need to remember. So thus the closed loop system would be stable need to be positive. So that means that KD should be greater than 0. Okay, and sorry. So we require the other two coefficients to also be of the same sign. So thus we need KD to be greater than 0 and KP plus 1 to be greater than 0. Okay, so we require these two conditions to be satisfied, right? So this would imply that KD should be greater than 0 and Kp should be greater than -1. Okay, so this is the range of the proportional and integral gain that would stabilize the closed loop system, right? So that's what we can observe from this analysis. So if we plot the controller parameter space, okay, so as Kp and Kd, okay. So what will happen is that if you look at Kd greater than 0, as we already know, this is this fastness, right? So that is Kd greater than 0. So this is Kd greater than 0, right? So if we are looking at Kp greater than -1, what we do is that like we draw a line at Kp equal to -1, okay, the vertical line passing through -1, okay, and this region is Kp greater than -1. So the feasible region, which is the intersection of these two regions, will be this. Okay. So this is the controller parameter. So the controller parameter space this region. Okay. So that is it is the region which is shaded in purple, which will essentially what to say ensure that the closed loop system is stable. Okay, using a PD control. Okay? So we can immediately observe that by looking at this procedure, right, by using the Rhodes criteria, Rhodes stability criteria, we are able to essentially have you know like the region of the controller gain for which we will get closed loop stability. Okay, and then we will go forward when we learn more concepts. We'll also figure out how do we get narrow down the controller gains even further, right? By looking at closed loop performance. Okay, so that's something we will learn as we go forward. If you recall, like we had looked at closed loop performance uh, by looking at what to say, parameters such as settling time and peak overshoot and getting sub-regions in the left of complex plane, right, where we require our closed loop pools to be located, right? So that will ensure that performance is met in addition to closed loop stability, all right? So that's something that is important. Fine. Okay. So any questions on this example? Okay. So then we will move on to the next topic. So one topic which is of importance is of analyzing the steady state error. So what is this analysis of steady state errors? So going back to our basic block diagram, please note, like this is something which is very important. Like I think I would have already pointed this one out to you, but let me draw the block diagram. So let's say this is the plant transfer function. U of s is the input and y of s is the output. Let us say we have the feedback path transfer function h of s, and we have the summing junction where we compare the reference input, uh, considering negative feedback. Okay, and then like we have the error which is passed to the controller block, which is P of s. Okay, so typically what happens is that, like as we know, the C of s times P of s is D of s, right? So this is taken as a single block. So this is typically the same block diagram is redrawn using this. Okay, so you will see an alternative representation, okay, of the same block diagram wherein the closed loop control system will be drawn like this. Okay. Okay, so you can see that rather than having a C of s and P of s in series, we just have what to say, G of s in the as a the forward path transfer function. Okay, so this is another way of drawing the same block diagram, right? So as we already know, we have already calculated the closed loop transfer function, and we also like essentially what to say, have you know so what to say, we have looked at how to analyze the closed loop stability by looking at the closed loop characteristic equation, right? We also see what is the open loop transfer function and so on, right? So to go ahead with this analysis of steady state error, first let us assume that the closed loop system is stable. Okay, that is the basic premise with which we started. So we start with the premise that the closed loop system is stable because, see, as I already mentioned, like you can immediately see that we have two requirements, right, from any control system design. So what are those requirements? The requirements are that, like we have the uh, what to say, we require the closed loop system to be stable, right? Point number one, right? Then we need to ensure that the closed loop performance is met. Okay, so these are the two requirements, right? So now, given these requirements, we need to figure out, like what, how we can analyze the steady state errors, right? But to analyze the steady state errors, the basic premise is that the closed loop system should be stable, right? Because without stability, there is no point in talking about performance. Okay, so analysis of steady state error falls in the realm of performance error, right? So we are analyzing the performance of the closed loop system by looking at the steady state error. And as we just discussed, we can talk about performance only if we have stability in the first place. Otherwise, it doesn't make sense, right, to talk about performance. So that's why we have this premise that the closed loop system is stable. So now, once the closed loop system is stable, we want to analyze the error. So we look at E of s. E of s is going to be equal to R of s minus W of s. Okay. I'm just looking at the block diagram. So W of s is going to be equal to H of s times Y of s. Okay, I'm just writing down each block one by one. And Y of s is going to be equal to G of s times E of s, right? So this is Y of s, correct? So we can immediately observe that this can be rewritten as R of s minus G of s H of s times E of s. Okay, so this one. So immediately we can observe that if we combine the terms involving E of s, we will have 1 plus G of s H of s multiplying E of s. That's going to be equal to R of s. Okay? So then we have E of s by R of s to be equal to 1 divided by 1 plus G of H of s. Okay, so this is what we have. Alright, for the ratio of the Laplace of the error signal to the Laplace of the reference input signal. Okay, so this implies that E of s is going to be equal to 1 divided by 1 plus G of s H of s, the whole thing multiplying R of s. Okay, so this is what. All right, I hope this is clear. Right, so this is how we get the error transfer function. Okay, not the error transfer function, the Laplace of the error. Okay, in terms of the reference input Laplace. Okay, so that's what we have. Now we use a property of the Laplace transform. Okay, so if we recall, if we use what is called as a final value theorem. Okay? So the steady state error, because we are looking at steady state error. See, what is steady state error? Let us say we tell, like, for example, like, let us say we have a fan, right? We specify that the rotational speed of the fan should be 100 RPM. So that is our reference input, right? Is it not? Now, if the controller starts acting and the speed of the fan starts going towards 100 RPM, right? So, and we wait for a sufficiently long interval of time, then the question becomes, like, what will be the error value? All right, so that's what we need to look at. So the steady state error, which is given by ESS, is going to be equal to limit t tending to infinity E of t, which can be rewritten as limit s tending to 0 is saying 0. Okay, so this is the final value theorem. Okay, so what did we use here? Okay, we have used what is called as a final value theorem to get this expression. All right. So if we substitute now for E of s, we are going to get limit s tending to 0, substituting for the f times R of s divided by 1 plus G of s. So, okay, so this is what we'll have. All right. Okay. So I hope it's clear how we got the expression for the steady state error. Okay. So we can immediately observe that this expression for the steady state error depends on the reference input signal R of s, right? Is it not? We can see that R of s comes into play, and consequently, the steady state error is going to depend upon what is the reference input that we will provide to the system. Okay, so that becomes very important. Okay, so in order to proceed further, let us consider the open loop transfer function to be of the form. So typically, the open loop transfer function can be written in this form. Okay, so we will see how. Okay, so let us say, like, of the form d of s h of s is equal to k naught times t1s plus 1, t2s plus 1, okay, all the way till some t and s plus 1, okay, divided by s power capital N tas plus 1, t ts plus 1, all the way till some tps plus 1. Okay. So the only thing is that, like, in the denominator, capital N plus capital P should be equal to small n, right? Small n is the order of the system, right? So that's something which we do, all right? So this is what to say, a general representation. We'll see how we can write this. Okay, K naught is what is called as the open loop gain. Okay, and the system, when written in this way, is what is called as a type N system. So what is a type N system? We can immediately see that this, of course, this N can be 0, 1, 2, etc. Okay, it is a non-negative integer. Okay, so it essentially means that it has N open loop poles at the origin. Okay, so that is what. Okay, so just as an example, if we have n to be 0, we call this as type 0 system. Okay, if we have n to be 1, we call this as type 1 system, and so on. All right, so that's what we have. All right, okay. So these are the various types, okay, of system within code. Okay, as far as this particular what to say, uh, representation is concerned, right? So we have these various types, okay, and depending on the value of capital N, okay, we can have what to say, different numbers of open loop poles at the origin, right? So just to take an example, let us say, how can we write in this way, like, let us say, we take some example, right? S plus 2 divided by S times, S plus 4, okay? So suppose if you want to write in this way, right? So what we can do is that I can take 2 common from in the numerator, so I will get 0.5 S plus 1, okay? And then in the denominator, I take 4 common, I will get 0.25 S plus 1, okay? 2 by 4 will be 0.5, so I will have 0.5 times 0.5 S plus 1, right? And I will have S times I missed S in the denominator. I will have S times 0.25 S. All right, so we can immediately observe that, the value of capital N is 1, all right, and we have written in that form, okay, which we have considered, right? So it is possible, okay, to write it in that form, okay. So that's what I wanted to demonstrate, okay, given any open loop transfer function, okay. So now the question is, given these facts, okay, and the expression for the steady state error that we have derived, we can immediately observe that the steady state error is dependent on the type of reference input that we would provide. Okay, so that is point number 1. So now the question that arises is that, like, can we analyze what will be the steady state error with different references? Okay, so that is the problem we shall consider. So let us do that. Okay, so first, as a first case, okay, let us consider a unit step reference. So what we are asking is that suppose if we are given a unit step reference input and we are asked to track it. Say for example, I took that example of a fan, right? So we are essentially given a unit step reference input. That means R of t is 1. Okay. So R of s becomes 1 by s. Okay. So suppose if I have to track that input, then the question becomes, like what happens to that input as a function of as time or what happens to the steady state error, right? As time t tends to infinity, right? So that's what we want to figure out. Okay, so consequently, if we want to get an idea about that, we can use whatever we have discussed above. So R of t in this case is equal to 1. So R of s becomes equal to 1 by s. Okay. So if R of s becomes equal to 1 by s, so what happens is the following, right? So what happens to the expression for the steady state error? So the steady state error, ESS, which is going to be equal to limit s tending to 0, s times R of s divided by 1 plus g of s h of s. That's going to be equal to limit s tending to 0, s times, now R of s is 1 by s, right? So we write 1 by s, and then like we put 1 plus g of s h of s. Okay. So once I have this these get cancelled out. So what will I have? We'll have limit s tending to 0, 1 divided by 1 plus g of s h of s. Okay. So this can be rewritten as 1 divided by 1 plus g0 h0. Okay. Where g0 h0, the quantity, is nothing but the limit s tending to 0, g of s h of s. Okay. So we just write it in that way. That's it. Okay. So that is limit s tending to 0, g of s h of s. This is defined as a term KTE. Okay. That is what is called as a static position error constant. Okay, so this is what is called as a static position error. Okay, so essentially we have the steady state error consequently to be equal to 1 divided by 1 plus k. Okay, so this is the steady state error while tracking a unit reference. Okay, so this is the expression for the steady state error uh, while tracking a unit step reference. Okay, so that's what we do. All right. So what is this KPE now? Okay, so now if we go back to this general way in which we wrote down the transfer function, right? G of s is k naught t1s plus t2s plus 1 and so on, right? So if we want to essentially look at what is this steady state error, like, and how do we what to say, look at this as a in a generic way. So if we look at this, right, what happens is the following, right? So recall that we have g of s h of s to be equal to that k naught times what to say t1s plus 1 all the way to tms plus 1 divided by s power n, right? Tas plus 1 to tps plus 1. Now let us say we have a type 0 system. So this implies that type 0 system. This implies that capital N is 0. So what can we say about KPE? So KPE, if you go up, suppose let us say capital N is 0, right? So this term is not there. right? Now, what is KPE? We need to take the limit s tending to 0, g of s h of s. So, if s power capital N is not there in the denominator, what will happen to g of s h of s if we substitute s equals 0?
K0 divided by K0. K0.
Uh-huh. Yeah. So essentially, if you look at it, you know, you look at this particular term, okay, you substitute s equals 0, right? You will have just k0, right? Because the way it has been written, like you substitute s equals 0, like all the terms will vanish in the numerator and the denominator, that is those having s. So we will just be left with k0, right? Is it not? Okay. So kpe will just be k0. Okay. So that's what we will have. All right. Now, what will happen then will be the following, right? So the steady state error will be 1 divided by 1 plus k0, right? I hope it's clear, right? How do we get the expression for the steady state error while tracking a unit step reference input for a type 0 system, right? So I hope it is clear how we got KPE to be K0 and the steady state error to be 1 plus K0. So now let us look at type 1 system. Okay, then I will come back to type 0 shortly. Okay. So type 1 system means capital N is equal to 1. So what can you say about KPE? Now let's go back to the expression for the open loop transfer function. So in the open loop transfer function, now capital N is 1. So we have a s term in the denominator. Now if I take the limit s tending to 0, g of s, h of s, what will I get? So there is a s term in the denominator, right? Is it not? So in the numerator, all the first order terms will vanish. In the denominator also, TA plus 1, TAS plus 1, TBS plus 1, all the way till TPS plus 1 will vanish, right? I will only have s power s in the denominator. So I will have k naught by s, but if I substitute s equals 0, what will happen to that parameter?
Infinity.
It will go to infinity, right? Isn't it? So KPE consequently will be infinity. So the steady state error is 1 divided by 1 plus KPE. So that will become 0, right? Is it not? Okay. So we can observe that this implies, this is a very important consequence, right? So for the type 1 systems and above, type 1 and above systems, type 2, type 3, and so on, right? The steady state error while tracking a unit step reference input would be 0. Step reference input in general. Okay. So, on the other hand, for type 0 system, the steady state error is 1 by 1 plus k naught. So, we need to increase k naught to make ESS as small. Okay. So, increasing k naught, which is what is called as the open loop gain, will lead to higher cost, okay, of the system. Okay. So, essentially, practically, it will lead to, what to say, either a costlier actuator or one with a higher range or something like that, right? So, I think those are things we need to consider, okay, or look at, okay. So, this is what we have. as far as tracking step input, right? So now let's connect the dots. So I made a statement, right? So that if you have integral controller under some conditions, you can guarantee what to say zero steady state error, right? For tracking step inputs, right? So please note that if we have G of S H of S, that's going to be C of S times P of S times H of S, right? So suppose, let us say, for the sake of argument, okay, like let's say H of S is 1, okay, and P of S is, let's say, 1 divided by S plus 1, okay. So immediately you can see that it's a type, that is the plant does not have an integral term. Suppose if I use an integral controller, a PI controller, so then I will have KPS and KI divided by S, and then I will have 1 by S times S plus 1. So the open loop transfer function will become KPS plus KI divided by S times S plus 1, right? So immediately we can see that N will be 1, right? This is a type 1 system, right? Correct? Is it not this example? So immediately you can observe this thing, right? So that is, if we have a plant, like wherein to begin with, we do not have what to say the system, all right, to have an integral term that may result in a non-zero steady state error. Sorry, that would essentially help in achieving zero steady state error with step input. What we can do is that, like, we can add an integral controller, and from today's analysis, we have figured out that the addition of an integral controller or integral term in the controller will lead to at least the value of capital N being 1, right? If we did not have an integral term in P of S and H of S. And from today's analysis, we can immediately see that the steady state error for tracking step reference inputs will be 0, right? For type 1 systems and above. So in summary, if you look at that, the steady state error for tracking unit step inputs, which will be 1 divided by 1 plus KTE. So if we were to write the summary, it will be 1 by 1 plus K naught for a type 0 system, okay, and it will be 0 for type 1 and higher system. Okay, so that's what we have. So this above, I can replace it with higher, that's a better. Okay, so we can immediately observe that we can achieve zero steady state error by having an integral term in the open loop transfer function. Consequently, if we do not have an integral term in the plant transfer function to begin with, we can introduce an integral term through an integral controller, and that will help in achieving like this desired property. Okay, I hope this is clear to everybody, right? So as to how we got the steady state error to be theoretically 0 with this integral control. Okay, so I hope now the statement which I made, like while discussing the integral controller is clear, right? So I told that, like an integral controller can guarantee a zero steady state error, right? So under certain conditions and while tracking step inputs. So now you can immediately connect a statement to this analysis, wherein we can observe that for a plant, like which does not have an integral term, or if we do not have an integral term in the feedback fast transfer function, if we add an integral controller, we will essentially have zero steady state tracking errors for step reference inputs. Okay, so that's very important. All right. Okay. Any questions on this? Okay. So in summary, if you want zero steady state error for tracking a step reference input, we require at least one integral term in the open loop transfer. So yeah, that can be introduced by using an integral control. Okay, so that's what we can summarize. Okay, from this discussion. Okay, so I think I will stop the discussions for this class here, and then like we in the next class we will look at what will happen when we want to track other classes of reference. Okay, and then like we will do further. Right. So I will stop here for today. Okay, thank you.